Hello, problem solvers. We're on lesson 19 now about primes and divisibility. And I'm going to start by doing the Euclidean algorithms. The first problem says pick two two-digit numbers and find their GCD, their greatest common divisor, by using the Euclidean algorithm. It says explain how the algorithm works. I'm not going to do that. It's in Journey Through Genius. It's in Zeitz, although the problem number on this ice sheet is probably from the second edition. But I'll just show you how to do this. So I chose 68 and 51, which I already knew in my head were multiples of 17. That's their GCD. So the way it works is you take the bigger number, and you're basically doing long division, but you're writing it out this way. So 51 would go in once. Basically not writing any fractions while you do it. And you would have 17 left over. You take this number and slide it over here, and this number, you slide it over here. So not the multiple part. That's the one you don't really care about. How many copies, you ignore that. So 17 times 3 plus 0. As soon as you get plus 0, this number that you brought over, this guy, that's the GCD. So that was pretty straightforward. 17 is it. And then I'm going to go ahead and do 52 and 53 matched with 68. So that one's maybe too quick to be illustrative. So if you did 52, well, you'd have 16 left over. Bring this over, bring this over. 16 times 3 would be 48, add 4. So the multiple is always the one you don't care about, so the times 1 times 3. Bring the 16 over, bring the 4 over. 16 is 4 times 4 plus 0. Every time you get a 0, that's the GCD. So 4 is the GCD for 52 and 68. 4 times 13, 4 times 17. And let's do 68 and 53. And then we'll stop. So times 1, and you'd have 15. And then bring over 53, and then 15 times 3, 45, you do plus 8. Bring over 15, and then you have 1 times 8 plus 7. Bring over 8 and 7, plus 1. And then bring over 7 and 1. So this is, I know I've been switching back and forth the order here, but I want to be careful here. 1 is the number I bring down, and then I'd have 7 copies of it, plus 0. 1 was the number I brought down. It's there. The GCD is 1. I should be more careful about which side I do these things on, but just keep in mind it's the number that you bring across. Those are the ones that matter. The multiple ones are the ones you don't care about. Alright, so we're going to use that on question 2. Question 2 says, you got this expression and you want to prove that it's in lowest terms for any integer n. So if this is n cubed plus 2n and n to the 4th plus 3n squared plus 1, that's another way to say that is that these are relatively prime. If they had a common factor, then you would just remove it, right? So if they never have a common factor, their GCD is 1. That's what it means to be relatively prime to each other. And so I want to divide one by the other. Now, I probably want to do the bigger one by the smaller one. I'm not trying to do long division or anything like that. I'm just trying to show that these two have a GCD of 1. And notice when I did all those numbers with 68, I chose the bigger one to be divided by the smaller one. Okay, so if I need to get, you can think about long division for a minute. Think about how we did partial fractions of long division. I need an n to get to n to the 4th. So what would that be? What would I have to add? It would be n to the 4th plus 2n squared. So I'd have another n squared plus 1. And this was the multiple. Like, that's the part that I said before, ignore. So n cubed plus 2n and n squared plus 1 come down. And how many multiples do I need? I think I need a multiple of n to get n cubed plus n. And then I would have another n. And again, we ignore the multiples. Bring that down. How many copies of n do I need here? Well, I need n. And that would be n squared plus 1. And so ignore the multiples yet again. I'm trying to keep them always the first thing. Then I'd have n, and then I'd have a 1, and I would need n multiples plus 0. This is the last one I brought down, so the GCD is 1. That makes them relatively prime, and that means that that is in lowest terms. It's a little bit harder when you have polynomials instead of numbers, but it's the same principle. Okay, so for question 3, it says find the smallest positive integer n that n over 2 is a perfect square. N over 3 is a perfect cube. And n over 5 is a perfect fifth power. I guess there's not a word for that. That's a little crazy looking. So, but you know that if these are integers, you have to be divisible by 2, 3, and 5. And we're trying to find the smallest positive integer, so we don't want to have other factors. We don't all 2s, 3s, and 5s. So we might as well say it's got some power of 2, it's got some power of 3, it's got some power of 5. And if we can find those out, we're good. Okay, so n over 2, I would make this go 1 less power. And I would do the same thing for 3 and 5. Now, I guess let me go ahead and write this out, just in case we need them. A, 3 to B, 5 to the C minus 1. Okay, so I want this first one to be a perfect square, right? That means that A minus 1 is even, right? So I'll focus on A first, and then we'll do the other ones. So that's a perfect square, so that has to be an even power. But then A is also, based on this, because it's a perfect cube, A is a multiple of 3 and 5. So I need a multiple of 3 and 5. Well, 15 is the first number that comes to mind. 15 minus 1 is 14, which is even. So 15 is the number that would work for A. Now let's work on B. B must be even because this is a perfect square. B minus 1 is a multiple of 3, and B is a multiple of 5. Okay, let's start with the easier parts. Even, multiple of 5. 10 is the first one that comes to mind. Subtract 1, you get 9. That's a multiple of 3. So B is going to be 10. And I'm really just doing this investigatively, right? I'm trying to get the smallest number that works. Okay, so then C is even. C is a multiple of 3. So I get a perfect cube. C minus 1 is a multiple of 5. And I think if C, 2 times 3 gives you 6. C minus 1 is 5, which is a multiple of 5, so C should be 6. Okay, so your final crazy answer, remember these are just the exponents, so n should be 2 to the 15th, 3 to the 10th, C to the 6th. That's a gigantic number, but that is the smallest number that does those things. Crazy. Alright, the last problem says true or false and why. The product of two consecutive positive integers cannot be equal to a perfect square. So I have two consecutive, so 1, 2, 3 consecutive positive. That would be, cannot be equal to a perfect square. So 4 times 5 is 20, and it's not equal to, remember perfect squares go like this. It's saying none of those numbers are ever the, well, if it's false, are ever the product of two consecutive positive integers. Okay. The thing you should know here, so a fun fact, is that consecutive numbers are relatively prime. This is an important number theory fact. So anytime you have a number n, an integer, and you have another number, the GCD is 1. Okay. So that means their product can't be a square unless both numbers were squares. So if I want, if I want n times n plus 1 to be a squared, the only way that's going to happen, the only way I'm getting those factors of a here is if these are both squares. Otherwise, this doesn't make sense. Because I'm not, it's not like I can get one copy of a factor here, like 1a, and then another one over here, because they don't share anything in common. But consecutive numbers are never perfect squares. Look at this list. Consecutive numbers are never perfect squares except for 0 and 1. But on this problem, they want positive integers. So there are no, or I should say perfect squares are not consecutive. So this is false. And that is the end of the ice sheet on primes and divisibility.